Welcome to the Pareto Polymath. We're dedicated to slicing through complex topics, delivering the essential 20% that empowers you to understand the greater 80%. In this video, we are exploring the nuanced craft of training machine learning models. Think of machine learning models as students who learn concepts from data examples, similar to how children learn by being shown pictures. We refer to these organized data sets as training sets. They provide examples like images, text, or other data for the model to find patterns. But how does the model know what insights to glean from this training data? The key is that machine learning algorithms are programmed to process the examples to mathematically uncover statistical relationships and properties. So the training data provides the lessons for the model to derive its own data-driven insights about the world. Of course, just ingesting lessons doesn't guarantee practical learning. You need to test and apply knowledge with fresh, unfamiliar cases. Hence, we use separate test sets to evaluate model performance on new, previously unseen data examples. This tests how well the model recognizes patterns in new data, not just the training examples. Think of test sets as pop quizzes. In evaluating model capabilities, some pitfalls can trip up naive learners, overfitting and underfitting. Overfitting occurs when a model becomes so focused on memorizing and mirroring the exact details of the training examples that it fails hopelessly when confronted with anything slightly new or different. It's like a student who aces practice exams but flounders on the test. Underfitting is when a model is so simple it doesn't capture the full range of examples, even in the training data. It's like a lazy student who retains very little from the lessons. Luckily, there are techniques we can use to coach our machine learning models towards wiser, more robust learning without these extremes. One powerful approach is cross-validation, where we intelligently split available data into different chunks and iterate through training and validating each chunk. Models trade off these roles like study groups exchanging tips before a big exam. This approach builds versatility instead of memorization. When assessing model capabilities, we must also look beyond any single performance number, like accuracy. Raw grades alone often fail to reveal the subtle strengths, weaknesses, and biases of a student's knowledge. Additional nuanced metrics like precision, recall, and F1 provide fuller insights into the model's performance. Of course, the training data itself also matters immensely. Models can only be as effective as the examples they learn from. Using outdated, narrow, or unrepresentative training data would be like learning medicine solely from 19th century books, or studying ocean life using one small pond. Real-world relevance is key. On that note, we'll end today's discussion here. In our next video, we'll dive deeper into the practical applications of machine learning models across industries. We'll also explore important implications as these systems grow more capable and ubiquitous. Until next time, keep exploring and learning.